Now that we know how to differentiate the exponential, let's look at rates of change. And that's what our derivative is. So very, very common application is this thing called growth and decay. You might have seen it in science. But it starts with a very, very simple assumption that the growth and decay is proportional to the population. It kind of makes sense when you think about it. The more people you have, the bigger the population, then the more the population is going to grow and the more the population is going to die. We can write it like this as a differential equation. The rate of change of the population with respect to time is equal to some constant times the population. In other words, it's directly proportional. That is the differential equation. Now, that model, we can apply to all sorts of things. Growth and decay. Radioactivity, a very common one that they use it for. Working out half-lives and things like that. Now, at this stage, we don't know how to solve it. So it's okay for us to just quote the solution. And the solution is simply this. The population must equal some constant times e to the power of kt, t being time. Here's a question from the 2015 HSC, which we can do. So we're looking at the amount of caffeine in the body. Decreases according to, and there's the differential equation. The c to t is negative because it's decreasing. 0.14 times c. C is in milligrams, T is in hours. So rather than asking you to find the solution to this differential equation, they've taken it from reverse and said, well, here is the solution, just show that it works. So that way all we've got to do is differentiate it and go, okay, go. So there's the solution they're telling me it is anyway. If we differentiate it, and what we saw about exponentials is we just differentiate the power and then that goes to the front. Well, the power is negative 0.14t. If I differentiate that with respect to t, we'll just get negative 0.14. So we have negative 0.14 times a e to the minus 0.14t. So yeah, we've got negative 0.14 times c, the solution they're suggesting. So it does work. It is a solution to that equation. Now pretty much from there we just use this equation to solve problems. So when t equals 0, so initially there's 130 milligrams of caffeine in the body. What is A? What is that constant? So we know when t equals 0, c is 130. We substitute it in, well, e to the power of 0 is 1, so a will equal 130. That brings up an interesting point about the solution. A will always be whatever the initial value is. Because when t equals 0, you're going to get e to the power of 0. So if you know the initial amount, you'll always know what that constant is. Now we have to work out, well, after 7 hours, how much caffeine's in there. So when t equals 7, we now know a is 130, and it's just substituting into that equation. Bit of calculator work, and we get 48.8. I've done mine to 1 decimal place. So 48.8 milligrams of caffeine remains in the body. So what is the time taken for the amount of caffeine in the body to halve? Which is very similar to that radioactivity question of what is the half-life? Same sort of idea. Okay, well, halfway would be when C is 65. Initially there was 130. So if we substitute it in, we get an exponential equation to solve. So we get e to the minus 0.14t is equal to a half. I want to make t the subject. So to undo the exponential, we log, we do the inverse. Because it's e we're talking about, so base e, it's important we use the natural logarithm here. So t will end up being minus 1 on 0.14 log of a half. I don't know if you recognise this from science, but that basically is the half-life formula, where it's always minus 1 on some constant number, depending on the material you're dealing with, times the log of a half. And that'll get you the half-life of different things. And a bit of calculator work. There we go, 4.95105. I've rounded that to the nearest hour. So it takes about 5 hours for the caffeine to halve. So that's the sort of questions they might ask us. So at this stage it really is just substitution into a formula, which sometimes got to work out what the formula is. But again, at this stage it's okay for us to just quote the solution.